I also would like to thank you all for attending this talk. So today I'm going to present my PhD dissertation entitled Timely Inference over Networks. So here is my brief educational background. So I completed bachelor's in electrical and electronic engineering from Bangladesh University of Engineering and Technology in yeah. Yeah, I think so.
Okay.
Yeah. So I completed my bachelor's in 2017, and then I started my PhD in 2018 in Auburn University in electrical engineering. And meanwhile, I obtained a master's degree in electrical engineering in 2022. So here is an outline of my talk. So at first, I will introduce remote inference system and its application towards network intelligence. And then I will also introduce age of information in remote inference systems. Then I will also discuss two topics. That is, how does data freshness affect remote inference or estimation, and how to improve inference performance. And lastly, I will conclude my talk by summarizing the contributions of my work to the research community. Due to the evolution of AI and communication technologies, we have numerous applications of networked intelligence systems, including vehicular networks, factory automation, remote surgery, UAV or robot navigation, augmented or virtual reality, real-time surveillance, and video analytics. Real-time inference or estimation is crucial in these systems. For example, an autonomous vehicle predicts the trajectories of nearby vehicles, and in remote surgery, doctor needs to know the movements of surgical robot. So we consider a remote inference system where a trained neural network is utilized to predict a time-varying target based on a sequence of signal observations called feature that are collected from a remote sensor. Due to communication delay, the delivered features may not be fresh. At time t, the freshest received feature was generated at time t minus delta t. This time difference delta t is the staleness of feature for inferring the time-varying target at time t. And this time difference is called age of information, or simply AOI. So in this remote inference system, the neural network we utilize is trained offline using pre-prepared training dataset that includes feature values, target values, and the time difference between the feature value and the target. And this time difference delta may vary across training data samples. Yeah.
I guess I have one clarification question.
Yeah, sure.
This delta T, is this something you assume is known? That you have some sort of time stamping that's known, or is that something you're inferring itself?
Yeah, so here the delta T in the receiver side, it is known. It's known because actually when it sends the feature, then it also sends the generation time of the received feature. And then in the receiver side, it can calculate the AOI, delta T.
It's like a timestamp.
Yeah, the time stamp, yeah.
Thank you.
Can you move this?
Well, actually, you'll change the view. You could minimize that.
You can minimize that.
Minimize.
So this one?
Yeah. Right, there you go. There.
Okay. Yeah. So the utilized neural network is trained offline using pre-prepared training data set. And this The time difference delta may vary across training data samples. And we use empirical risk minimization based supervised learning algorithms for this offline training phase. And in online inference, we fed feature values and AY values into the neural network to infer the time varying target in real time. To measure the performance of the neural network, we can use different loss function. So this loss function is chosen based on the goal of the application. For example, in softmax regression, the neural network generates a probability vector for the classification task. And in this case, we can use logarithmic loss function or log loss. And in minimum mean squared estimation, we can use quadratic loss function to measure the performance of the neural network. Now, to measure the performance of the remote inference system, we can use inference error, which is the expected loss over the joint distribution of the target and the feature. And given AY value equals to delta and feature length L, this inference error can be expressed as a function of the AY delta and the feature sequence length. Now, I will define the age of information for wireless communication networks. At time t, the age of information is the time difference between the current time t and the generation time of the freshest received packet. To understand more about age of information, let's look at this figure. Here, SI is the generation time of the ith packet and DI is the delivery time of the ith packet. So before time t, if we consider all the samples before time t, then the ith packet is the most recently delivered packet. Hence, at time t, AY equals to t minus SI. The AY increases linearly over time, and whenever a new packet delivers, it drops, and then the AY again grows. So there is another related concept which is called delay. Here I show the delay of the packet I plus 1, which is the difference between the delivery time of the I plus 1 packet and the generation time of the I plus 1 packet. So we can observe that AY is a metric for the receiver side, and it is a function of time. However, the delay is a function of the data sample. Now, this concept of AY has attracted a lot of attention to the research community. Earlier studies analyzed and optimized average AY, peak AY, and monotonic functions of AY. Earlier studies developed scheduling and sampling policies to minimize average AY, peak AY, and increasing functions of AY. However, there was still a lack of understanding regarding how to evaluate the importance of fresh information in real-time systems. So towards this end, we have two questions. That is fresher data always better? We proposed a new information theoretic tool to evaluate the importance of fresh information on remote inference system. And by using this information theoretic tool, we explain when fresh data is better and when it is not. And the second question is how to improve inference performance. So we designed scheduling policies based on the insights from information theoretic analysis to minimize inference error. Now consider the first question. Is fresher data better? So earlier studies assumed system performance degrades monotonically as feature becomes stale. So the earlier studies only made this assumption. But it is not always true, as we can observe in many machine learning experiments. So during my PhD, I have conducted 6 machine learning experiments. Out of them, 3 experiments are provided in this slide. So in video prediction, we can see that inference error is an increasing function of AOI. That means fresher data is better. However, in temperature prediction and reaction prediction, it may not be always true. For example, in predicting the temperature, next hour temperature, the temperature recorded 24 hours ago is much more relevant than temperature recorded 12 hours ago. So for this reason, when the feature length is equals to 1, we get that inference error is a non-monotonic function of AY. But if we increase the feature length to 24 and use the past 24 hours of observations, we can see that the inference error becomes a monotonic function of AY. Now consider the reaction prediction problem. So consider that a vehicle initiates braking, and then the nearby vehicle does not respond immediately due to the reaction delay of the driver or the delay of the braking system. And hence, an outdated action, a slightly outdated action, is much more relevant than a current action to predict the reaction of the leader vehicle. So to illustrate this phenomenon, we simulated a leader-follower robotic system where the follower robot follows a delayed state of the leader robot because of this communication delay. And our goal is to predict the follower robot states, or we can say the reaction of the leader robot by using the state of the leader robot. And then in this case, we observed that a slightly outdated information of the leader robot is much more better than a fresh information. So these two experiments tells us that fresher data may not be always better in many practical systems. So we need to explain when it may happen by using information theoretical analysis or any theoretical analysis. Now, because a neural network function is complicated, it is difficult to interpret the experimental observation by using the inference error equation. So we take the help from information theory metric for inference error, and we use L conditional entropy. The L entropy of a random variable y is the minimum expected loss for predicting y. And the L conditional entropy is defined as that given x, the minimum expected loss for predicting y is the L conditional entropy of y given x. Now, if L is log loss, then we get Shannon conditional entropy. If L is quadratic loss, then we get minimum mean square error. Now, for any loss function, we can have an L conditional entropy. And our work holds for different loss function and different L conditional entropy. So we also obtain that this inference error is lower bounded by the L conditional entropy. And also the inference error is very close to L conditional entropy, and this closeness is measured by using the KL divergence between the distribution of the training dataset and the inference dataset. And as we will see later, that it is convenient to analyze the L conditional entropy than the inference error equation. Now we'll analyze the L conditional entropy with respect to AY. So here we'll use data processing inequality for Markov chain. So if the data sequence is a Markov chain, then the L conditional entropy is an increasing function of AY for a fixed feature length. However, practical data in experiments can be non-Markovian. So we need to extend the data processing inequality to non-Markov chain. We extend the data processing inequality to non-Markov chain by using a local information geometry method. Specifically, we propose a new epsilon Markov chain model. Here, given epsilon greater or equal to 0, 3 random variables y, x, and z are said to be an epsilon Markov chain if the Shannon conditional mutual information of y and z given x is less or equals to epsilon square. This epsilon Markov chain measures the divergence of a data sequence from a Markov chain. So if epsilon equals to 0, then the epsilon Markov chain is also a Markov chain. If epsilon is far from 0, then the data sequence is far from Markovian. Now we're ready to answer the first question. So we use epsilon Markov chain to get an epsilon data processing inequality. By using the epsilon data processing inequality, we get that the L conditional entropy equals to an increasing function of AY plus big O epsilon. So if epsilon equals to 0, then this L conventional entropy is an increasing function of AY. If epsilon is far from 0, then the L conventional entropy may not be monotonic with AY. So this theorem implies that for Markovian data, pressure data is better. For non-Markovian data, pressure data is not always better. Now, by using this theoretical analysis, we interpret the experimental observation. So in this video prediction experiment, the video data sequence is close to Markov chain. And hence we get that this inference error is an increasing function of AY and fresh data is better. But for temperature prediction and reaction prediction, the data sequence can be far from Markovian. And hence we get the fresher data is not always better. So we interpret this by using the tools from information theory and local information geometry, as we have explained before. So, yeah.
How do you determine something like temperature data when you say it's not Markovian?
So basically,
Like atmospheric conditions there?
yeah, we have considered different atmospheric conditions. And so basically what the data Markovian means, like, for example, if you have this 12 hours of data, 12 hours before
Not
data.
depending on like all past that, it's on the most current.
Yeah, on the most current.
Could you add more states to the dynamics and turn it into a Markovian system?
Yeah, if I can add the many history, then it becomes Markovian, right? So like, for example, when we have a 24 hours observation, then it becomes Markovian. And we have that fresh feature is better.
So it would depend on how you structure the data in your models.
Yeah. So if you can have a Markov data, then you have a fresh data is always better. Now there is a problem, like you need to add more information. So sometimes more information may not be useful for remote inference system because it takes more communication resources. So I will explain that later. Okay. So we also use an analytical model to explain when fresh data is better and when it is not. So here we can, where we have used an analytical model and we have a closed form expression. So we can get the L conventional entropy and we have this minimum mean square error. So these two metric matches each other, are the same. And here the target is to predict the time varying target YT, which is related to a signal value VT. So this VT is generated using an autoregressive model with order 4. Now in this problem, if we use feature length equals to 1, then we get that the epsilon value is far from 0. And that means the data sequence is far from Markovian. And we get that this minimum mean square error is non-monotonic with respect to A1. Now, as we increase the feature length, then this epsilon value becomes equals to 0. And it becomes, the data sequence becomes close, it becomes Markov. And hence this minimum mean square error tends to an increasing function of AY delta with the feature length increasing. So this tells us that for a Markovian data, we have fresh data is always better. But for non-Markovian data, fresh data is not always better. But if we increase the feature sequence length, we can have Markov data sequence. And then the fresher data becomes better. However, actually, if you have more a longer feature, it needs more communication resources, like it needs more time slots to for the delivery from the transmitter side to the receiver side. So in this case, actually, the second question comes that how to improve inference performance. So we use inference error as the performance metric to design timely communication protocols for remote inference system. And we design optimal feature selection strategies and scheduling policies to minimize inference error. Now we have some observations that I have discussed earlier a bit, that firstly, for non-Markovian data, fresher data is not always better. And here is the thing that longer feature reduces inference error. Also, for the longer feature, you may have fresher data is always better. And as you can see that the inference error decreases as the feature length increases in this channel state information prediction. But longer feature requires more communication resources, which may not be good for remote inference system. For example, a longer feature can take more time slots to reach the destination and ends up being stale, which may result in worse performance. So based on these observations, we propose a new selection from buffer status updating model. So in this model, the transmitter stores B most recent observations in the buffer. And then the scheduler has the option to decide when to send and which packet to send. If the scheduler decides to send at time t, then the scheduler also needs to decide if the feature is longer or shorter, if the feature is fresh or stale. The feature sequence length determines if the feature is longer or shorter. And the starting position B of the feature in the buffer determines the fresh or stale. And we call this starting position feature position in rest of the slides. And this model is more general than generated-at-will model, which is used in the AOI literature. And in this generated-at-will model, the scheduler has the only option to send the freshest observation, that in this case, which is the VT. And when the buffer size equals to 1, the selection from buffer model reduces to the generated-at-will model. Now we solve the scheduling problem with fixed feature length to minimize the expected time average inference error, where this penalty function is the actual inference error, which can be either monotonic or non-monotonic with AOI. And the scheduler decides the sending times and the feature position, that is fresh or stale. So earlier studies assumed only monotonic AOI function and determined only feature sending times. Therefore, our scheduling problem is much more difficult than the earlier studies. To solve this problem, at first we fix the feature position. That is always send the bth oldest packet in the buffer, and then we optimize the feature sending times. And our theorem states that it is optimal to send next feature when the previous feature is delivered, then the channel becomes idle and an index exceeds a threshold value beta. And this beta is the unique root of a fixed point equation. So we can get this threshold value by using a low complexity algorithm like bisection search. Moreover, we get that this threshold beta is exactly equal to the optimal objective value of this sub-scheduling problem. Now, how to get this theorem or how to get this index function? So we use a restart in random state formulation to get this theorem. So now we discuss restart in random state problem. So in our model, a feature can take random time slots for transmission. Whenever a new feature delivers, AOI starts from a random state as the feature position plus the random transmission time. So this problem becomes when to restart from a random state. And in the literature, we have restart in state problem, and which is solved by using Gittins index-based threshold policy. So when we have this formulation, we guess that, so our solution could have also some index-based threshold policy. Towards this end, we use the similar idea of the restart in state problem and get an Bellman equation of our restart in random state problem. And we simplified this Bellman equation and get a simplified equation. And by directly solving this equation, we get the index function. And we prove by using dynamic programming method that this index-based threshold policy is optimal. And this is the first work to connect this AOI optimization problem with the restart in random state problem. So now we can state the optimal scheduling policy with fixed feature length. The optimal scheduling policy has very nice structure. It always sends the B star's oldest packet in the buffer. So that means the feature position, the optimal feature position is time invariant. So when before the system starts, we can actually determine the optimal feature position, and we can use that optimal feature position for all time slot T. Also, the optimal scheduling policy sends the next feature when the previous feature is delivered. That channel becomes idle, and an index exceeds a threshold value mu. And this threshold is exactly equals to the optimal objective value of this problem. And it is the minimum of the optimal objective value of the service scheduling problem. So this one, and over different feature position. Now, how to get the optimal scheduling policy with time varying feature length? So we will not fix the feature length now. To solve this, we need to also determine feature length at every feature transmission time, along with the feature sending times and the feature position. The optimal feature length cannot be obtained using a closed form equation. So the optimal feature length is obtained by using the following Bellman equation, which requires some relative value function. And by using the previous theorems, we can simplify the policy iteration algorithm to get this relative value function. And after getting the optimal feature length, we can use the optimal waiting time or sending time and the optimal feature position associated with the optimal feature length. So numerical studies suggest that our optimal scheduling policy with feature length selection reduces the inference error by up to 10,000 times compared to the periodic updating and generated at will zero at policy. So we plot average inference error versus a parameter alpha that determines the transmission time. So if this parameter alpha is small, so that means that we can send a longer feature in shorter time. Here the load is less. And by sending the longer feature, we can achieve 57,000 times performance gain compared to other policies that does not use longer feature. And when this parameter alpha increases, the load becomes high and we cannot use longer feature in shorter time. So in this region, we only use the optimal waiting time and the optimal feature position and get 26 times performance gain. So in this region, the optimal feature length is 1. And when we also plot the average inference error versus the buffer size. As the buffer size increases, the inference error also decreases and we get 11,000 times performance gain compared to the generated at will model that does not use any buffer. But here we can see that at some, if we increase buffer furthermore, like we increase buffer size, we can actually stop increasing buffer size because further increase does not help us more. So at this point, we have the optimal scheduling policy for the single source, single channel. Now, naturally, we have the third question. That is how to design optimal scheduling policy for multi-source, multi-channel system model. Here we consider that we have M source predictor pairs connected over N communication channels. And each source has BM most recent features. And due to the limited number of communication channels, a centralized scheduler needs to decide which sources to select and which feature from the sources buffer to send. And in this model, we assume that the feature transmission time can be random, but the feature transmission are non-preemptive. So that means if a channel serving one feature, it needs to finish serving that feature before it can serve a new feature. We also assume that a source can be served by at most one channel at a time. For example, if one source is now a feature from the one source is currently transmitting, then we will not transmit another feature from that source, even if there is some channel. So now we solve the scheduling problem with fixed feature length to minimize the summation of the expected time average inference errors for all sources, subject to a channel occupancy constraint. That is, the total number of occupied channel cannot exceed total number of channel in every time slot t. And the scheduler decide which sources to select and which features, that is fresh or stale feature, from the selected source to send. So this problem is a restless multi-arm bandit problem with multiple actions. So this problem called restless because even if we do not select a source, the AY of that source will continue to increase. And this problem is multiple action because we have more than binary choice of the features. We can have more choices of the features. Like if the buffer size equals to more than 1, then we have multiple action problem. So this restless multi-arm bandit problem is known to be p-space hard. Earlier studies in AY literature considers monotonic AY function and binary action and utilizes visual index to get asymptotically optimal scheduling policy. But for multiple actions, we cannot only utilize this visual index to get asymptotically optimal policy. So we propose a new policy integrating visual index and with duality-based feature selection. So the standard restless, so now I will describe how to get that. So the standard restless multi-arm bandit considers equality constraint. And to fit with the standard restless multi-arm bandit, and we have the inequality constraint. So to fit with the standard restless multi-arm bandit, we add n additional dummy bandits. And each dummy bandit occupies one channel for one time slot if selected or scheduled. And each dummy bandit does not incur any cost. So because we have n additional dummy bandits, which is equals to the number of total channels, and each dummy bandit occupies one channel for one time slot, we can have this equality constraint from the inequality constraint. And because the dummy bandit does not incur any cost, so the policy that optimizes the main problem, it also minimizes the equivalent problem. Next, we relax the part-time slot constraint to time average constraint, and we apply a Lagrange multiplier to the constraint. And then we can decompose the problem to m+1 decoupled problems, where we have m per source problems and one problem for dummy bandits. For each per source problem, we need to minimize expected time average inference errors plus a channel occupancy cost, where this dual variable lambda is the one time slot channel occupancy cost. Now we will use visual index for the source selection using this decoupled problem. And evaluating visual index requires closed form solution to this decoupled problem. And an indexability condition needs to be satisfied. And this indexability requires a nice solution structure to the per source decoupled problem. So each per source problem is a Markov decision process with two states. One is the AY of the source and the amount of time used to send the current feature from the source M. And it is denoted by this value beta. If beta equals to 0, no feature from the source M is currently in service. If beta is greater than 0, a feature from the source M is currently in service. Then we define a passive set, which is the set of states delta beta, such that if the AY equals to delta and beta t equals to beta, that means beta amount of time is used to send the current feature from source M, then it is optimal to not select the source M. So the passive set means that, so this is the set of states where will not select the source optimally for the optimal policy. And the mth decoupled problem is indexable if this passive set increases with the increase of the cost lambda from negative infinity to infinity. Now, this decoupled problem is very similar to the single source, single channel problem. And we have index-based threshold policy for this problem also. And because the solution to the part source problem follows an index-based threshold policy for a channel occupancy cost lambda, we were able to simplify the definition of the passive set by using this index value and this threshold value. Moreover, this threshold increases as the channel occupancy cost lambda increases. By using this, we can prove all decoupled problems are indexable. Now, as we proved the indexability, now we need to get the Vidal index. If we cannot prove the indexability, then the Vidal index actually does not make any sense. So after proving the indexability, we get the Vidal index. This Vidal index is the minimum channel occupancy cost for which this state value belongs to the passive set. So that means Vidal index is the level of channel occupancy cost lambda such that the selecting or not selecting the source is equally profitable. And we get Vidal index for each source in closed form. So if beta is greater than 0, then Vidal index is negative infinity. If beta equals to 0, then we obtain closed form expression from a simplified definition of the Vidal index, which is the infimum transmission cost when this index value is less than the threshold value. And we also get that for dummy bandits, Vidal index equals to 0. And this is the first work to obtain Vidal index for non-monotonic AY function, random delay channel, and multi-action problem. Now we are ready to state the proposed policy with fixed feature length. So for all time slot t, we select sources with maximum Vidal index. And sources with negative Vidal index is never selected. So this is because we have dummy bandits, n dummy bandits, that is equals to the number of the total channel. And the Vidal index of the dummy bandits equals to 0. So the dummy bandits will be given higher priority than any source with negative Vidal index. So the sources with negative Vidal index will be never selected. And if source M is selected, we send a B star mth oldest feature, which is the optimal feature position of this decoupled problem, which is associated with a optimal Lagrange multiplier of a dual problem. To get this optimal Lagrange multiplier, we use stochastic subgradient ascent algorithm. We can use this stochastic subgradient ascent algorithm in offline or online. So we have this algorithm. And we prove that our proposed policy is asymptotically optimal as the number of sources and channels increases to infinity, maintaining a constant ratio. We prove this theorem by using linear programming based priority conditions. Now we also have proposed we have a policy for time varying feature length. However, indexability is difficult to establish for this problem, and we cannot have Vidal index. So we propose a new policy that does not require indexability. We call it maximum gain fast policy. Here for all time slot t, we select sources and features with maximum positive gain index. So this gain index is defined as the action value for not selecting and minus action value for selecting. To summarize my work, so we use inference error as the performance metric to design timely communication protocols. And this inference error is a function of AY and feature length. And we get that for Markovian data, Fréchet data is always better. For non-Markovian data, Fréchet data is not necessarily better. And longer feature reduces inference error, and longer feature needs more communication resources. So longer feature may not be good for remote inference system. So we need to optimize this timeliness and this feature sequence length. Towards this, we propose a new selection from buffer model we propose we get optimal single source, single channel scheduling policy. We get new asymptotically optimal multi-source, multi-channel scheduling policies. And the proposed solution reduces inference error by 10,000 times compared to some periodic updating and generate at will zero weight policy. So I also contributed to status updating with two-way delay channel, non-IID channel, and safety monitoring systems. I also contributed to AI for agriculture, and I served as a teaching assistant in machine learning and reinforcement learning courses during my PhD, and also maintained an online repository on Age of Information. So I have completed 8 papers in my on this work, and 2 papers are under preparation. In future, I want to continue research in wireless networks and information freshness. I am interested in semantic communications, restless multi-bandit problem, online scheduling, and reinforcement learning problem. I want to implement my theory to UAV or robots. Thank you.
Thank you for the presentation. All right, so I think we can first let the general audience ask question to Cameron.
Yeah,
After
sure.
that, we will just the professors and faculty members can ask questions.
Am I included in the general audience or the professor side?
Professor Sam.
I mean, I'm not committed, I was.
Okay, all right. So, you guys as students, if you have any question for Cameron, anything about the slides, any notation, any experiment, and any questions? Does me, do you have any question? You have any question? So I'd be the same, okay. Ask questions, and then you can interact with us, because if you don't ask questions, we have to excuse you guys. Have no questions? Sam, you have no-
Hi, can you hear me?
Yeah, so I think one.
Okay.
Yeah.
cool.
Hi, Kamran. Yeah,
Hi.
nice presentation. I have
Thank
one
you.
question for the machine learning training. So, how can we train a model that considers such a AOI impact?
Okay.
Yeah.
So actually, you can collect the dataset first, or the time series dataset, and then you can divide different datasets with different AOI values. So you can, for example, you have a dataset with YT and XT. Then actually you can have XT, YT, and XT minus delta. You can prepare the dataset for different AOI values.
I see. But
And
will
then
that
actually you can
Uh-huh.
combine all of the dataset. We have actually 2 ways to do that. Actually, you can use different neural networks for different AOI values, or you can have one single neural network that is trained using a large dataset that includes these AOI feature values and target values and these AOI values.
Yes, so my concern is that if you combine all the combination of these AOI values, will that cause the curse of dimensionality as
Yeah.
the
Yeah. So because you have, so rarely is that AOI value will be very large in the real-time system.
yeah.
So for this reason, you can actually have a truncated AOI values.
Makes sense.
That actually depends on your real application. So you can have like AOI value equals to 20. Sometimes you can also have AOI value equals to 100. That also depends on your time slots and also your applications.
I see. Thank you.
Yeah, thank you for the question. Yeah.
Okay, so I see you have some nice pictures of your family. You
Yeah,
want
yeah,
to
I
talk
want
about
to-
technology?
Yeah, sure. So I want to have some acknowledgements. So at first, I would like to express my sincere gratitude to my advisor, Professor Yin Sun, for his continuous support, help, and guidance during my PhD. Yeah, he was always a very good professor and good human being to me. Yeah. And yeah, so I also want to thank my committee members and reader and my collaborators. I have many collaborators. I Actually, I was fortunate to have many collaborators. Yeah. And then I also want to thank my heartfelt thanks to my family, my wife, Tasmin Jawan Orni, and also my brother, my sister, my father, and my mother. And without them, it would not be possible for me to actually complete these works. Yeah. Thank you all. Thank you.
Okay, very nice. So any more questions from the audience? Okay. So in that case, then please